Hello guys, so welcome back to our labs. This is the seventh lab now. Okay, we're gonna continue the hub of rectifier, but now we're gonna add one simple addition, which is this capacitor. Okay, we learned it from our lectures that this smoothing capacitor or the peak capacitor will enhance a lot our rectification, and it will really will increase the amount of DC in the load, the 100 resistor load here. Okay. Uh, Another addition, which is this switch, and this switch is just closed or open, and you can close it or open it while the circuit is running. You don't need to close or turn off the simulation and rerun it after changing the switch from open to close or close to open. Another change here, I'm gonna use this source. It's called AC voltage. It's different from the AC power sources that we used each time. And the difference is that you can just define the maximum value, the peak value. So here, for example, the output here is 15 volt peak and minus 15 volt in the minimum, or in the minus, in the negative half cycle. Okay, we're gonna test this circuit in three situations: when the switch is open, so the capacitor, or I'm sorry, so the resistor, the load will not be connected to the capacitor. Then we're gonna close this switch and try the circuit with this capacitor in here. Then we're gonna again close the switch, but it changes the capacitor to 470 microfarads, not 1000. And we learned it in the lectures that whenever you increase the capacitor value, the capacitance, this will enhance more the output. If you decrease it, the DC will decrease, as we will see now, and we're gonna verify that. So let's run now the circuit, the simulation, and send the oscilloscope to these settings in here. So let's set this to DC, YT, YT, 10 volt, 10 volt. Everything is perfect. And look now at the output. Okay, this is the input. Basically, how can we know that? This is the node. This is the color of this node, the input node. And this is the color of the voltage at the capacitance, which is the channel B here. It's in blue. Okay, and as you see, our output is perfect DC. And the reason, as we learned in the lecture, since this switch is open, the capacitor is just, I'm sorry, the resistor, the load looks like infinity to the capacitor. So the capacitor will not discharge its charge in the load because it's open in here. So it will keep its voltage forever. Okay, let's measure this voltage. So if we go in here, this is basically the output. I'm sorry, the channel 1. So let's go to, so the maximum of channel 1 is 14.8. Let's now measure our DC. Our DC is the channel B. So let's select the trace at the channel B. And look, so the output is 14.5. Okay, so the difference is around 0.5, 0.6, just like what we learned in the lecture. We learned in the lecture that the maximum here should be Vmax, and this value should be Vmax minus 0.7. Okay, and the difference, as you see, in around 0.5, something like this. This is basically the measured value. Good. So now we're gonna close the switch. So just guys, remember such shape, because we're gonna compare the output that we gonna get when we close the switch to this one now. Okay, let's close the switch. Let's rerun this guy. Okay, now we get it. Look now. Now the capacitor charge, then discharge, charge, then discharge, charge, then discharge, and so on. Okay. And this is basically, the normal output that you're gonna see, because basically in your applications you will have a resistor in the output. You will not have an application. You need this rectifier to feed some load with a DC voltage. So the normal case is that you will have here a load. Okay, it's not infinity, and you will have such ripples, we can say. So let's look at the output alone without the input. So this is the output alone, which is called the ripple. Okay, It's much better than the half wave rectifier output. Okay, but just these rebels we need always to to decrease them. Okay, so let's now make some measurements. We're gonna measure the rebel minimum. So this point in here, this is the minimum. So we're gonna move this marker to the minimum. So the minimum is 12.26. Let's measure the max. The max is 14.1. Okay, so we can now measure the rebel peak to peak, because it's this point, as we learned in the lecture, the voltage rebel peak to peak is this point, the maximum minus the minimum. Okay, and we can also determine the rebel theoretical. I mean, the rebel peak to peak. We know that the the rebel voltage peak to peak, as we learned in the lecture, can be theoretically calculated using this equation: V max minus 0.7 over RCF. R is 100 ohms. C is 1000 microfarads. And F is 60 hertz. Okay. So basically, we can also determine the theoretical values. Then we can here determine the error. Okay, which is basically this guy, the theoretical minus the measured, like the equation in here. Good. Now we can also measure the DC. This is something that I didn't explain in the lecture. So here we have also a DC. Still, this is not a perfect DC, but our DC now is the average value between the max and the minimum. Okay. So basically, imagine it as a line passing the DC. Imagine it as a line or a constant, line like this, passing through the average or the point between the max and the minimum. So we can determine VDC measured as variable maximum minus variable peak to peak over 2. Okay, which is basically the average value between this value and this value. Okay, and the average value is variable max minus plus variable minimum divided by 2. Okay, so you have two options: either averaging, which is this point plus this point over 2, or you can say it is the DC is variable max minus variable peak to peak, which we just measured in here, over 2. It is exactly the same. You should get the same stuff out of these two equations or two ways or two methods. Okay. Okay, we can also measure, the DC theoretically. So this is basically, I'm sorry, this is what I've explained is measured. Okay. We can also measure the DC theoretically. So we know theoretically variable peak to peak. So VDC theoretically is V max minus 0.7. This point should be V max minus 0.7 minus variable peak to peak, which is a theoretical value here, divided by 2. So the DC measured is, you have two ways to measure it. Either this point, the maximum point, measure it, minus variable peak to peak, which we just measured from the previous step, over 2. This is the first way. Okay. The second way, the theoretical way, which is V max minus 0.7. Okay. Because this point should be V max minus 0.7, but you might, in the measurement, it might not be V max minus 0.7. It might be a little bit deviated, because we say that the diode have 0.7 all the time when it conduct, but this is not true all the time. It will have some value closer to 0.7. Okay, might be a little bit less, a little bit higher. So the theoretical value is V maximum minus 0.7 minus variable peak to peak over 2, and variable peak to peak is this value in here. Okay. Good. Now the second step is to change the capacitance to 470 microfarad. And I want to just you guys to remember such a shape. So we have here a little bit of small, small rebels. Let's now change the capacitor and decrease it, and you will see that this rebel will increase basically, because here, look at this. When C decrease, V rebel will increase, which is bad. So let's stop that guy and double click in here and set that to 470. So you're gonna repeat what you have done in 5 here. So you're gonna measure again VDC, the measured value, okay, at 470. So you just repeat what you have done in 4 and 5, okay? So you get VDC measured, then you recalculate, the theoretical value of VDC. So you will just use the same equation here, but you will just replace this C with 470 microfarads, okay, and measure again the error, okay. So it should be a simple experiment for you guys, okay. You may be a little bit confused about VDC, I know, because what we have done in the measurement, it's exactly the interpretation of the equation. But the equation assumes, for example, that the higher value, the maximum value is V maximum minus 0.7. So don't measure it. So in the theoretical, the V maximum is 15 because we know the input is 15. Don't measure it. And we assume all the time that the diode drop is 0.7, although it might be a little bit less, a little bit higher. And variable peak to peak is measured using this equation, okay. And another thing here is this equation is approximate equation. So you will find that the error in that case when the capacitor is 1000 microfarad is less than the error when the capacitance is 470 microfarad. And the reason is, if you go back to the lecture, you will find that when we derived this equation, we assumed that RC is very big. Okay, so we assume all the time that RC is very big. So whenever you decrease, so when you have RC is very big, let's assume infinity, this will give you, the perfect approximation. I mean, the approximation will be very close to the real measurement. But whenever you decrease C or R, okay, you will see that you are deviating from the actual measurement. And we should see here an error higher than the error in that case. The error is not that big, but it's still higher than the error in that case. So you can check on yourself. If you get here error less than here, then you have something wrong in your measurement. Okay. Thank you guys for watching this video and see you in the next lab. Bye-bye.